Let's go over response curves. This is going to be an important part of your exam. You need to be able to interpret these curves to give an answer. So let's take a look at a typical dose-response curve. So on the vertical axis, you can see that this is the percent of maximum effect, and on the bottom, you have a log scale of the dose. So you can see here a competitive inhibitor. Your agonist is your drug alone, and you add the antagonist, and it causes an agonist plus competitive antagonist change or shift in the curve. So when we say that there's a shift in the dissociation or binding curve to the right, what we're really talking about here is that you've got some kind of competitive inhibitor. Compare this to a non-competitive inhibitor or an antagonist. So here you can see there's an agonist plus an irreversible antagonist, and what happens is your percent of activity is reduced by, in this case, 50%, even though the dosages are starting out at the same point. So notice the difference. The competitive inhibitor shifts the entire curve over to the right. The non-competitive inhibitor, also called an allosteric inhibitor, reduces the maximal impact of that particular drug, but starts at the same concentration. So dose-response curves can be logarithmic or non-logarithmic. Here is an example of the same drug portrayed in two different ways. The top is the absolute value, and the bottom scale here is the logarithmic value on the horizontal axis. The effective concentration that causes the maximal effect is called the Emax. So in both cases here, we've got the red line at 100%. The effective concentration or effective dose that produces 50% of the maximum effect is called the EC50. So you can see here on our logarithmic scale, the EC50 is much easier to pick out. On our absolute scale, it's very hard to pick out because it's shifted so far over to the left. A binding curve is very similar. It's slightly different but similar. So drugs that bind to receptors follow a sigmoid-shaped log binding curve. The effective concentration or effective dose that results in 50% of the receptors being bound is called the dissociation constant, or KD. The smaller the KD, the greater the binding affinity of the drug, and the greater the KD, the weaker the binding affinity of that particular drug. Quantal curves are very similar, but now instead of talking about how many receptors are being bound or how much of a maximal effect you have on the system, we're now talking about populations. So a quantal curve tells us the effect of a drug in a population. Once again, it follows that sigmoidal curve. So the effective concentration that results in 50% of the population being affected is also referred to as E50, but sometimes we call it an EP50, or effective population 50% activity. Let's look at the concept of spare receptors. So spare receptors are when you have extra receptors out there. They are not occupied even at the maximum effect. So in this particular case, even though not all of the receptors are occupied, you've already achieved a maximum effect by occupying a certain percentage of the receptors, and you have these other receptors that are left over. Let's talk about toxicity curves. Toxicity curves are using the dose-response curve and the kill-response curve. So in the case of a dose-response curve and the toxicity being death, you can look at these two curves and show that the therapeutic ratio, or the ratio between the dose at the effective dose and at the toxic dose, and you divide those two numbers, that'll give you your therapeutic ratio. The therapeutic ratio is used all the time. So we know, for example, that labetalol, which is a beta blocker, has a very wide therapeutic ratio. You can give as little as 100 milligrams or as much as 2,400 milligrams a day. Wide therapeutic ratio means we have lots of ability to titrate the drug. A narrow therapeutic ratio means that we only have a small ratio to deal with. So for example, bisoprolol, which is another beta blocker, we only can use 5 or 10 milligrams. We don't really have a lot of other choices. Let's talk about potency. So here's an example of a statin. statin called rosuvastatin or Crestor. It is the most commonly used statin in the world today. Atorvastatin is another statin that works very, very well. It is not as potent as rosuvastatin, but you can see that the maximal effect is almost the same. You just need a higher dose to get it. Simvastatin is an older statin. It is not as potent, and it is not as effective at maximum dose. And pravastatin is probably the oldest in this graph, and you can see that it is the least potent drug. It is also the least effective. So it's important to know, for example, that Crestor ranges in dose between 5 and 40 milligrams. Atorvastatin ranges in dose between 10 and 80 milligrams. Simvastatin really is an 80 milligram pill. And Pravachol or pravastatin is also an 80 milligram pill, or 160 milligrams in some cases. So when you're talking about the maximum doses and minimum doses, that gives you the dose response curve. But within each drug, they can have different levels of potency. Okay, let's do a question. This is a potency curve question. The dose response curve below represents 4 beta blockers. Response refers to the percentage of patients who responded to the drug. Answer the following questions as true or false. These are quantile curves. Is that true or false? Yes, they are. So a quantile curve represents a population curve. So if your response is the percentage of patients who respond to a particular drug, that's a quantile curve. The next question, drug B is the least potent drug. Is that true or false? That's false. So drug B is actually the most potent drug. Don't be fooled by the fact that the maximal effect is less than the other drugs. The fact of the matter is that it takes a very small concentration to elicit a response. The amount of response is irrelevant to the potency question. Drug B is the most effective drug in a population, true or false? That's false. So drug B is the most potent, but it is probably the least effective because you can see the top of the curve ends up at about 50% of the other drugs. B is a very potent drug. B is half as effective as the others. Okay, let's keep going with more questions. The dose-response curve below represents 4 beta blockers. Response refers to the percentage of patients who responded to the drug. Answer true or false. The E50 of drug B is greater than the E50 of drug D. So we're talking about the red curve and the black curve. Which one has a greater E50? So the answer here is false. Clearly, that is not the case. Drug D is more titratable than drug C. Okay, this is a hard one. Take a look at the curve in drug D. We're not asking potency. Clearly, drug C is more potent. We're not asking about efficacy because clearly they have the same efficacy because they top out at around the same level. We're talking about titratability. And you can see that the slope of C is much more shallow than the slope of D. That tells us that we're able to adjust doses much more easily with drug C. So this answer is wrong. Drug C is the more titratable drug. And we can also gain an inference of the therapeutic ratio in the sense that we probably have a wider therapeutic ratio with drug C. The following statement is true. Pick the correct or true statement. The smaller the KD, the greater the binding affinity of a drug. B, KD represents the concentration at which 50% of the drug is ionized. C, a drug has a minimal effective concentration of 10 units per mil with a therapeutic ratio of 5. That means that the toxic dose is 2 units per mil. And D, the EC50 represents the point at which 50% of a population will have a toxic response to a drug. Which is the correct statement? Good. The answer is A. The smaller the KD, the greater the binding affinity of the drug. B is wrong because KD does not represent 50% ionization. That's pKa. KD represents binding. C is wrong because the division was in the wrong direction. The toxic dose is actually 5 times 10, which would be 50. And D is wrong because EC50 does not represent the toxic response, it represents the therapeutic response. Okay, I know those are hard questions, but I think you did very well. Good luck on your exams.